in which inflow is running parallel to, counter to, and close proximity to the outflow for some distance. And therefore, this is a very good example of countercurrent mechanism which is functioning in the kidneys. Basically, countercurrent mechanism can be divided into two parts. The first aspect of countercurrent mechanism is countercurrent multipliers, and these multipliers are loop of Henle. The second aspect of countercurrent mechanism will be countercurrent exchangers, which is vasa recta. I hope you remember what is vasa recta. We have studied the blood vessels of juxtaglomerular nephrons, and we have seen that they form long loops in the medulla surrounding the tubules, isn't it? They form long loop-like structures. These are vasa recta. So we will be dealing with this portion exchangers later on. First of all, we'll be studying what are countercurrent multipliers and how do they help in multiplying. So the factors that contribute to build-up of solute concentration in the renal medulla are, first of all, the active transport of sodium chloride and potassium ions from thick ascending limb of loop of Henle into the medullary interstitium. This portion is the most important portion for development of the concentration gradient. The thick ascending portion of loop of Henle, it has got a very important channel, sodium, potassium, blue chloride channels, and they are causing active transport of these ions and thus causing reabsorption of these ions in the from the tubules. Second thing which also adds up to the osmolarity is the active transport of ions from medullary collecting ducts into the interstitium. So you can see this is the medullary portion of the collecting duct, and various ions, they get reabsorbed from this portion also into the interstitium. Next will be the passive diffusion of urea from medullary collecting duct into this interstitium. So urea, this portion, medullary portion of the collecting duct is very, very permeable to urea. So that also gets passively diffused into the interstitium, and diffusion of only small amount of water into the medullary interstitium. All the water do diffuse into the interstitium, but that is small amount of water diffuses in the interstitium. Most of the water gets diffused in the cortical portions of the nephron. Most of the places where the water is being diffused is the cortical portions of the nephron. So small amount of water gets diffused in the medullary portions, but main things which are causing the development of osmolarity is this particular channel in the thick ascending segment of loop of Henle, then active transport of these ions, NaCl also in the medullary portion, and the passive diffusion of urea in the medullary interstitium. This table is showing the summary of tubule characteristics. We have studied this in the previous lecture, how various portions of the tubules are permeable to different substances. PCT is permeable to both the solutes and to water. The important aspect only I'm going to highlight here, and that important aspect is that thin descending segment of the loop of Henle is permeable to water, very much permeable to water. It is not permeable to other substances. The next important thing which you should remember is thick ascending segment of loop of Henle is permeable, very much permeable to NaCl or other ions as well. So it's very, very permeable to solutes, we can say. And the third important aspect is that inner medullary collecting duct is very much permeable to urea. If we remember these three things, it will be very easy to understand how the gradient develops in the medulla. Okay, so again, I am repeating, thin descending segment of loop of Henle is permeable to water. Thick ascending segment of loop of Henle is very much permeable to solutes, and inner medullary collecting duct is very much permeable to urea. So coming to countercurrent multiplication system, which I told you is loop of Henle, it is a process in which small osmotic gradient established at any level of loop of Henle is multiplied into larger gradient. So a small osmotic gradient has to be developed at one particular level, and once this gradient is developed, it is going to be multiplied to a larger gradient. Okay, so where is this small gradient being developed? This is the place. This is the place, thick ascending segment of loop of Henle is the place where a small gradient develops, and this is known as single effect. That means active transport of sodium and chloride out of thick ascending limb is causing the single effect. And secondly, we can also see that the thin descending limb of loop of Henle is permeable only to water. Okay, so this is particularly known as single effect. That is, these channels, sodium potassium 2 chloride channels lying here, continuously works to actively pump these substances, and they reabsorb these substances from the tubular fluid into the cells and then into the interstitium. Okay, so this is the single effect, and gradually this effect gets multiplied. Now here I am considering a hypothetical situation. If we assume that this is a loop of Henle and the osmolarity of the fluid present throughout the loop of Henle and in the medullary interstitium is uniform. Uniform means 300 milliosmoles per liter, because that is the osmolarity of the plasma. The plasma is being filtered and it is entering the tubules. So if we assume that initially the osmolarity of everywhere, each place is same 300 milliosmoles per liter, because plasma is entering the tubules and plasma have this particular osmolarity, and all the portions of the loop of Henle as well as the medullary interstitium is having the same osmolarity. Now this transporter, as I told you, the transporter which is present in the thick ascending segment of loop of Henle, that is sodium potassium 2 chloride channels, they are working. And once they are working, what are they doing? They are trying to reabsorb sodium, potassium and chlorides actively from the tubular fluid. And by doing this, they are going to produce a gradient of about 200 milliosmoles per liter. Okay, so they are going to transport the solutes from the tubular fluid into the medullary interstitium, and thus they start generating a osmotic gradient of about 200 milliosmoles per liter. You can see here, this portion now becomes 200 milliosmoles and this portion becomes 400 milliosmoles, because so many solutes are reabsorbed here. And as we all know, water cannot be reabsorbed from this portion of the tubules. So only solutes are being reabsorbed. And due to the reabsorption of solutes, the osmolarity in the medullary interstitium increases to 400 and it decreases in the tubular fluid in the ascending. It becomes 200. Okay, so this is the single effect which is taking place initially, the first step. Again, I am repeating, the first step is the movement of ions through sodium potassium 2 chloride channels present in thick ascending segment of loop of Henle, and due to movement of these ions, the osmotically active particles, they start moving from the tubular fluids into the interstitium, thus raising the osmolarity of interstitium to 400 and decreasing the osmolarity of the tubular fluids to 200. And the capacity of this gradient is always 200 milliosmoles per liter. They make a difference in between these two surfaces. 200 is the difference which they can create. So that much gradient is established due to single effect. Now we also know that water can easily diffuse from the descending limb of loop of Henle. And how the water diffuses? Osmotically. So the main role of water is to maintain the osmotic balance, isn't it? So when the water is coming through the thin descending limb of loop of Henle, it tries to maintain the osmotic balance. So water will move out till the osmolarity here becomes equal. So now we see that descending limb of loop of Henle also becomes 400, gains the osmolarity of 400, because that much water comes out of the descending limb so that it equilibrates with the osmolarity of the medullary interstitium. Okay, so this descending limb loses water and it reaches the same osmolarity as that of medullary interstitium. Next step will be the entry of new fluid in the loop of Henle. So now new fluid, because constantly we know that the fluid is entering the tubules. So new fluid is now entering the tubules. And as we all know, the new fluid is the filtered plasma, which has the osmolarity of 300. So now this new fluid is going to push the existing fluid. It pushes it. So 300 milliosmoles fluid which is entering is pushing the fluid which was present earlier. So now the lower portion gets 400 milliosmoles. It is pushed to this side also. So this lower portion is also 400 milliosmoles. And the other one, which was 200, is pushed up. All right. So I hope it is clear. With the entry of new fluid, you can see some amount of gradient being formed, isn't it? New fluid is 300 milliosmoles. The fluid which was present earlier of 400 is pushed down. It is pushed this side also, and the other one which was 200 is pushed up. Again comes the role of water being diffused from the descending limb, equalizing the osmolarity of the tubule and the interstitium. Now the water constantly diffuses out till it equilibrates with the osmolarity of the medullary interstitium. So we can see that this portion of medullary interstitium becomes same as that of this, and similarly here. So this portion, the upper portion becomes 300 milliosmoles, lower portion becomes 400 milliosmoles. But this pump, sodium potassium chloride channels, this particular pump is constantly working. It has not stopped working. So this transporter pumps out sodium and chloride again into the interstitium. As it is pushing the solutes again, it will cause increase in the osmolarity again. So till now you have seen that osmolarity in the tubules, this side is 200 and lower down it is 400. But due to this constant working of the pump, this osmolarity is going to change. Again, there will be a difference of 200 milliosmoles. And this is the change. Now the osmolarity of the tubules, upper portion becomes 150. This portion becomes 350. A difference of 200 you can observe here. Similarly, a difference of 200 you can observe in the lower portions also. So because of the constant working of this pump line here, again a gradient is developed. Again, a difference of 200 milliosmoles is developed here, right? Now what will happen? Again, the descending limb, where the water is permeable, it is going to equilibrate it. Again, it will cause the same osmolarity becomes equal to that because of the movement of water of the interstitium, right? Next, again, inflow of new fluid in the tubules. This keeps on going on. So this process is keeping on continuing, isn't it? 300 osmoles of plasma again enters the tubule, pushes the other constituents which were already there. So you can see now the 300 is entered here. Initially 350 was in the upper portion, it has pushed down. 500 has been pushed down. 500 has reached this portion of the tubule also. And similarly, you can see what is happening here. And at the same time, the water is trying to equalize the osmolarity, whatever is there of the tubules with that of the medullary interstitium. Okay, now this mechanism keeps on and on and on. So this is keeping on and it goes on till it multiplies many times, and transporters is constantly working. These transport, as you can see in this figure as well, they are constantly working, again causing a maintaining a difference of 200 milliosmoles here. And now you can see what gradient has been developed in the tubules, what gradient has been developed in the medulla, right? So transporters work again and again to reach a gradient of 200 milliosmoles, and this process will be repeated again and again. Thus, a single effect gets multiplied. Okay, so again, the single effect was there, started in the thick ascending segment of the loop of Henle, and it gets multiplied. In this figure, we can see it has been reached to 600, but in actual circumstances, it keeps on and on and on till at the tip of the medulla, we get the osmolarity of 1200 milliosmoles per liter. Okay, so that is the counter current multiplication taking place, starting from the single effect in the thick ascending segment of loop of Henle and going on multiplying with the entry of new fluids in the descending limb, pushing the other existing fluids down, which are pushed in the ascending limb as well. Continuous movement of this pump sets up a gradient, as you can see here in the medullary interstitium. So what we see in the countercurrent multiplication system is that an axial gradient is established. You can see this figure of kidney. Outer portion is the cortex, inner one is the medulla, and you can see the gradient being developed from 300 here to 1200 here. This is the gradient being developed, and this gradient is developed in the medulla. You can see the medullary portion has the increasing gradient. Usually cortex just contains the Rubens capsule, and only filtration is taking place here, so it has the same osmolarity as that of the plasma, 300 milliosmoles per liter. So this is the axial gradient, develops in all the throughout the kidney, and the magnitude of this gradient depends on various factors. First will be the rate of fluid flow. that if the fluid flow is very fast, there will be less time for the solutes to be reabsorbed. Okay, so if there is a rapid rate of flow of fluid, less amount of solutes can be reabsorbed, so that much gradient cannot be developed. If the speed of flow of fluid is slow, more amounts of solutes can be reabsorbed and a more amount of gradient can be developed. Second thing is the strength of single effect. Obviously, if it is strong enough, more amount of solutes are being pumped inside, then obviously the gradient will be more. Length of loop of Henle, if the length is more, if loop of Henle's are longer, they will tip inside and more variation in the gradient will be observed. Okay, so these are the factors which influence the development of gradient. So this particular gradient will be developed in the renal medulla. So what we have seen, what are the net effects of the countercurrent multipliers? So we have finished with countercurrent multipliers. So what is the net effect? More solutes than water is added to the renal medulla. That's what was observed in the countercurrent multiplier. That is, solutes are trapped in the renal medulla. The solutes are being trapped because they are being reabsorbed and they're continuously being trapped in the renal medulla. The fluid which is passing out from the ascending loop is diluted, isn't it? Because all the solutes are being reabsorbed. So whatever fluid is now exiting the ascending limb and going to the DCT, they are now diluted. And the gradient of solute concentration, which is established by the active pumping of NaCl, that is the single effect, is now multiplied by the counter-current flow of fluid. So this is the gist of whatever counter-current multiplier has done. So due to the counter-current multiplier system, solutes are trapped in the medulla, fluid which is passing out from the tubules now is diluted, and a gradient of solute concentration which was initially developed has now multiplied. Now there is very important substance, urea. So what is its role? It tries to maintain the osmotic gradient. Okay, the role of urea is to maintain whatever osmotic gradient has been developed due to countercurrent multipliers. This is maintained by the urea. It promotes the extraction of water and it also raises the intraluminal concentration of NaCl. Now how the urea works, how the urea cycle is there and how the urea helps in this. We know that urea is passively reabsorbed in PCT as well, but very 50% almost is reabsorbed in the PCT. So this particular urea then moves down to other portions of the tubules. And in the presence of ADH, water is reabsorbed in DCT and CT, concentrating urea in these parts. So when the fluid, the filtrate, it passes to DCT and to collecting ducts, here due to action of ADH, we all know that water is reabsorbed, and when water gets reabsorbed, the substances present here, they get concentrated. So the urea gets concentrated in this portion. Okay, so this portion, the medullary portion of the collecting ducts, is very much concentrated of as far as urea is concerned. So inner medullary collecting tubule is highly permeable to urea, which diffuse interstitial. So this urea, I had shown in that table also that this portion, the medullary portion of the collecting tubules, is very much permeable to urea. So we can see that urea gets reabsorbed through this portion, it enters the interstitium, then it gets secreted also at various places in the loop of Henle. But it is getting very much reabsorbed in the medullary portion of the collecting tubules. ADH also increases urea permeability of medullary collecting tubule by activating urea transporters. So there are certain urea transporters seen here, UTA1 and UTA3. These are urea transporters which also helps in the transport of urea. They are also activated by ADH. Okay, so urea, since it is passing, it is so much of urea is being reabsorbed here. Some portion gets secreted, but most of the urea gets settled here in the medulla. That also adds up to the increase in osmolarity of the medullary interstitium. Okay, so that is all about the countercurrent multipliers and the formation of gradient, medullary gradient. As we have seen how the osmolarity keeps on increasing as the fluid passes down and how the medullary interstitium becomes the concentration gradient develops in the medullary interstitium. Now coming to the next aspect, and that is countercurrent exchanges. Now suppose if there is a straight tubular blood vessel, as we see in various organs, blood vessel is just a straight tubule. What will it do? It is going to maintain whatever water and solute imbalance is there in that particular tissue. If there is more water in that particular tissue, it is going to absorb water. If there are more solutes, it is going to absorb solutes. Okay. If it is a straight blood vessel, and that is there in most of the portions of the body, there's a straight blood vessel. It just tries to balance the osmotic gradients. It tries to either absorb water or solutes or whatever is the difference in the gradient, and that gets balanced. But this is not the case in kidneys. In kidneys, we do not have the straight blood vessels, especially in the juxtamedullary portions, which goes deep inside the medulla. They are U-tubes. You know, vasa recta, they are U-channels. They are surrounding the tubules and they are in a U shape. They are not straight tubules. So what are they doing? They act as countercurrent exchangers. If you just concentrate on this figure, this yellow portion is the loop of Henle. What we studied till now is 300 milliosmoles of the fluid is entering the loop of Henle. The descending in the descending limb of loop of Henle, so much water is being reabsorbed and the concentration keeps on increasing till the tip. It is 1200 milliosmoles per liter. And as the fluid goes up, again, the concentration keeps on decreasing. What you see surrounding it is vasa recta. This red colored vessel is vasa recta. It is also U-shaped, surrounding the loop of Henle, and the fluid is moving in the opposite direction. Please pay notice to this. Vasa recta, the entry of fluid is from this side, and the exit is from the opposite side. Okay, so vasa recta, the fluid is moving in the opposite direction. So it is also countercurrent. Two parallel limbs moving side by side. Movement is in the counter direction. Okay, so what is it doing? You can see here that this is the thick ascending segment of loop of Henle, and we all know that sodium chloride, potassium are reabsorbed in these portions. So the amount is more here. So vasa recta is going to take it up. So these substances, these solutes are going to go inside the vasa recta at this portion. And as the fluid, as the blood passes in the vasa recta and goes in this portion, since water is being diffused from the descending limb, this water is going to diffuse inside the tubules. More here, the water is going to diffuse here, and solutes are less, so solutes will move out from this portion of the vasa recta. Okay, so what is it doing? It is exchanging. It is exchanging the solutes, it is exchanging the water, right? So vasa recta, I'll repeat this mechanism again. Vasa recta act as countercurrent exchangers. The flow of vasa recta is opposite to the flow of loop of Henle. Loop of Henle, this is the direction of flow, and in vasa recta, this is the direction of flow. Okay, so it will take up solutes while the blood is flowing down the vasa recta. It will take up solutes here and then throw water this side, and when it is moving up, when the blood is moving up, it will take up water and throw away solutes. Thus, it is acting as an exchanger and trying to maintain the osmolarity which was developed by countercurrent multipliers. Okay, so it is a countercurrent exchanger. The blood flow, although is very low in the vasa recta, the descending vasa recta loses water, gains solute, and ascending vasa recta loses solute and gains water. Okay, and thus it acts as countercurrent exchanges. So vasa recta or the countercurrent exchangers, they are trying to maintain the solute gradient which was created by loop of Henle. Okay, so the solute gradient which was created by loop of Henle is maintained by vasa recta. This we have already discussed, that in the descending limb of vasa recta, the solute diffuses into vessels, and in the ascending limb, solute diffuses out of vessels. So we have already seen in the previous figure. Thus, solutes keep circulating, and water diffuses out of descending limb and into the ascending limb of vasa recta. This we have also seen in the last figure. So while solutes recirculate in medulla, the water is removed from the medulla, and thus it helps to maintain the osmotic gradient. Due to the presence of vasa recta, the solute are recirculating. By recirculating, we mean it is entering one of the limbs of vasa recta and coming out from the other limb of vasa recta. Okay, and when the vasorecta is moving out of the medulla, it is taking away water with it. So it is removing water from the medulla, and thus it is helping in maintaining the osmotic gradient, which was developed by countercurrent multipliers. I hope it is clear till now. This is a very important aspect. Countercurrent system is very important aspect because this is the most important function of the renal tubules, that is concentrating the urine. So we have studied countercurrent multipliers, which were Lupo-Fenley, and countercurrent exchangers, which are vasorecta. So due to the differential reabsorption of substances, this graph is showing the changes in osmolarity of the tubular fluid. As the fluid passes through proximal tubule, the osmolarity remains constant because we know in PCT, the solutes are being reabsorbed and water is also being reabsorbed accordingly, so that the osmolarity doesn't change. The fluid which is in the tubules in PCT are isoosmotic to plasma. As we go down the loop of Henle, the osmolarity keeps on increasing. We have seen in the loop of Henle, the descending limb is permeable to water and hence the osmolarity keeps on changing, but in the ascending limb, it keeps on decreasing. So in the loop of Henle, the osmolarity, there is variation in osmolarity. At the tip of loop of Henle, there is maximum osmolarity of 1200 milliosmoles. And as the fluid exits, the osmolarity decreases to a great extent. It is low in diluting segments in all the cortical portions. And when in the collecting duct, it keeps on increasing until in the urine, the osmolarity again increases due to the effect of ADH also. The same summary is written here. What all portions are absorbing what many substances and how it is altering the osmolarity. This we have already dealt with in the figure, so I'm not repeating here. Coming to the next very important aspect, and that is diuresis. By diuresis, we mean excess excretion of water in urine. And this happens when there is failure of mechanisms that concentrates urine. Okay, so there will be excess excretion of water in urine, and that is diuresis. Basically, diuresis can be either water diuresis. That is, when there is excretion of large volumes of water without loss of excess of solutes, as happens in ADH deficiency. Okay, in ADH deficiency, there is excretion of large volumes of water without loss of excess of solutes. So that is water diuresis, when only water is being lost. Second type of diuresis is osmotic diuresis. When there is increased concentration of osmotically active particles in tubular fluid, then that is osmotic diuresis. So when these particles are more, they cause increased excretion of water also. Whenever we know that water follows the solutes. Okay, so whenever there is increased concentration of osmotically active particles in the tubular fluid, they increase the excretion of water as well. So that will be osmotic diuresis. Typically seen in diabetes when there is increased amount of glucose and great amount of glucose is filtered in the tubules, which cannot be reabsorbed from the tubules. That is, when the glucose exceeds the tubular transport maximum, then glucose will be there in the tubules, and in turn, it is a very important, very good osmotic agent. So it pulls in water and causes osmotic diuresis. That's why you observe polyuria in diabetes. Next is mannitol administration. This also is a osmotically active substance. So if we want to create osmotic diuresis, we can administer mannitol. It will not be reabsorbed, it will be secreted, it will be filtered, not be reabsorbed, and it will be an osmotically active particle, which will cause osmosis and removal of diuresis. It will cause a diuresis by removing of water. Right? So there are basically two types of diuresis. Water diuresis due to removal of large amount of water, and osmotic diuresis due to presence of osmotically active substances in the tubular fluid, which pulls water along and causes removal of water. Here in this graph, you can see water diuresis in a human after ingestion of 1 liter of water. So this dotted line is telling the point where a person drank 1 liter of water. Okay, so if a person drinks 1 liter of water, what will happen to osmolarity? The osmolarity of the fluid will, plasma osmolarity will dip, right? It will fall to a great extent. And what will happen to urine flow? It will increase to a great extent. But the urinary solute concentration will remain constant. Okay, it was just due to injection of water, so that much extra water will be excreted out, but the osmotic concentration will be maintained. So water diuresis can be due to excess injection of water also. Now, diuretics are the substances that increase the rate of urine flow. In various conditions of the body, in various diseases, we need to increase the rate of urine flow. We need to increase the excretion of water from the fluid. So in those conditions, diuretics are the drugs which are used to increase the urine flow. They aim to reduce the extracellular fluid volume by decreasing the total body NaCl content. We know that if we stop reabsorbing the main constituents, that is NaCl, even water will not be reabsorbed and it will be eliminated. So that is the main principle on which these diuretics are based. They try to stop the reabsorption of these important ions and thus stop the reabsorption secondarily of water and reduce the ECF1. So coming to the type of diuretics, first of all, come to most efficient ones known as loop diuretics. They are known as loop diuretics because they are located at loop of Henle, the thick ascending limb of loop of Henle, and we are very much familiar with this important ion channel working here, sodium potassium 2-chloride channel. We know that how important this channel is and how much reabsorption of solutes this particular channel do. Okay, so if this channel is blocked, this is going to cause a lot of changes, because if this particular channel, which is causing maximum reabsorption of sodium, potassium, and chloride, if this is blocked, these ions will remain in the tubular fluid and thus will prevent the reabsorption of water in further portions, because the concentration of these solutes will increase further when the tubule flows further, and the water will also stay with it to maintain the osmotic balance. So substances which are used to block this particular channel are known as loop diuretics. They are also known as high ceiling diuretic because of their efficiency. They are very, very efficient. They are blocking the most important channel in the tubules, the sodium potassium 2-chloride channels. Some of the names are given here if you want to remember, otherwise it's not that important. But these loop diuretics, they act at loop of Henle, blocking a very important channel present in the thick ascending segment of loop of Henle, and thus prevent the reabsorption of these ions, increasing the osmolarity of the tubular fluid, and thus causing the water to be retained there and then eliminated from the fluid. Coming to the next diuretic, these are, okay, this loop diuretics are used for various diseases. It's not necessary to remember, I've just mentioned it. Next type of diuretic is thiazide diuretic. Now these diuretics are acting on distal convoluted tubule. And if you remember, the important channel which is working in DCT is sodium chloride co-transporter. So if any substance can block this particular channel, they are going to increase the concentration of these ions in DCT and thus prevent the water to be reabsorbed in this portion and helps in diuresis. So these are thiazide diuretics. These are acting at the level of DCT and causing the diuresis. They are used to treat hypertension and edema. Another class of diuretics are potassium sparing, or we can say aldosterone antagonists. You know where the aldosterone acts? Aldosterone acts at the late portion of DCT and in the collecting duct. And I hope you remember what is the role of aldosterone. The main role of aldosterone is to reabsorb sodium and to secrete potassium. This is very important, you must remember this. So aldosterone is causing reabsorption of sodium and secretion of potassium. So if any substance can block aldosterone or is an antagonist of aldosterone, what is it going to do? It will prevent the reabsorption of sodium and it is also going to prevent the secretion of potassium, right? So prevention of sodium reabsorption is going to increase the ions in the tubular fluid and thus helps in diuresis. On the other hand, It is also preventing the secretion of potassium, so it is conserving potassium also in the body. Therefore, it is also known as potassium sparing diuretic, right? So the other name of potassium sparing diuretic of the aldosterone antagonist is potassium sparing diuretics. Okay, so I'll repeat here. Aldosterone acting on DCT and collecting duct is causing reabsorption of sodium and secretion of potassium. So if there are antagonists of aldosterone like spironolactone, they are going to block this mechanism, so sodium will not be reabsorbed and hence help in diuresis, and potassium will not be secreted and hence it will be preserved. So it is sparing potassium from being excreted. Even sodium channel blockers can also act here, and they also produce the same mechanisms. These are some of the sodium channel blockers which also act in a similar way, blocking these channels and work in the same mechanism, right? So these are another class of diuretics acting on DCT and collecting duct, aldosterone antagonists or sodium channel inhibitors, also, and these are also known as potassium sparing diuretics. They are also used in various conditions, in aldosteronism, primary or secondary hyperaldosteronism, etc., and various other conditions. It's not that essential. Another class of diuretics are carbonic anhydrase inhibitors. They inhibit the activity of carbonic anhydrase. If you remember, what is carbonic anhydrase doing? It is doing that carbonic anhydrase we have studied in various systems. What is it doing in the cells? Combining carbon dioxide and water to form carbonic acid and then dissociating into hydrogen ions and bicarbonate ions. And we have already studied in PCT that sodium hydrogen antipode is a very important mechanism working here, where sodium is reabsorbed and hydrogen is being secreted. So this hydrogen is coming from the activity of carbonic anhydrase, where carbonic acid is dissociated into hydrogen ions and bicarbonate ions. Hydrogen ions is secreted, bicarbonate is reabsorbed. Okay, so this particular channel will be inhibited because now hydrogen, this carbonic anhydrase activity is blocked, so hydrogen will not be secreted, and as a result sodium will also not come inside. Okay, so it decreases hydrogen secretion and increases sodium excretion, and thus helps in the diuresis. Okay, so these are the drugs, acetazolamide or Diamox commonly known as. They affect this particular counter transport of sodium and hydrogen in PCT, although their efficiency is not very high. It's not very high efficient things, but still they are there. They also cause diuresis to some extent. Okay, so now coming to the summary of all the diuretics which we have studied till now, starting from the PCT, proximal convoluted tubule, we have just now seen carbonic anhydrase inhibitors. They act here by affecting the sodium hydrogen antipode. They cause some amount of diuresis here. Then osmotic diuresis also occur in PCT because PCT is the main site of reabsorption of solutes. And if a solute is there which is not being reabsorbed, osmotically active substance, maybe glucose, maybe mannitol or whatever, then due to osmotic effect, again diuresis can happen here in the PCT. Then as we go down the loop of Henle, there's nothing here for diuretic purpose. As we move up in the thick ascending segment, very important diuretic, loop diuretics, high ceiling diuretics are acting here. Sodium potassium 2-chloride channels, they are blocking this particular channel and their efficiency is very high. So these are loop diuretics working in the loop of Henle. As we go to DCT, sodium and chloride channels, co-transporter is blocked by thiazide diuretics here, right? Then as we go further to the distal portion of the tubules and in the collecting ducts, aldosterone antagonists are acting as diuretics, and they're sparing potassium also, so they're known as potassium sparing diuretics. And as we go lower down, ADH antagonists, if given, they are also prevent the reabsorption of water and thus cause diuresis. Okay, so these are the various diuretics which we have studied. They are acting at various locations and thus causing increase in excretion of water. I'll repeat again, carbonic anhydrase inhibitors are acting at PCT. Then osmotic diuresis is also acting here. Loop diuretics in the loop of Henle, high efficiency diuretics they are known as, thiazide diuretics in DCT, aldosterone antagonists in the collecting ducts, and also ADH antagonists. So that's all for today.